Okay, let's talk about some application problems. I don't know if you guys have used this program. I had a student yesterday, had an office hour meeting, and she was using this program called Colanote instead of Notability. I hate Notability, but it's the best one I've got. And she was using this, and I thought I would give it a try, and I'm not loving it so far. Like just setting this up for today took me a lot longer than it should have. I don't know. Has anybody ever used this before?
I have not.
Okay, I just want to talk about some application problems, some linear applications. First one we've already talked about before, just a basic population model. There are a whole bunch of different population models we could do. In fact, for project one, I did a mock, like a sample project one that I'll post next week. And I go through a bunch of different population models. And this is the most basic, or they're more basic than this. You can have constant population, but the second most basic is assuming our rate of change of our population is proportional to our current population. The more people you have, the faster the population grows. That's a linear DE. It's also separable. It's also exact. There are a bunch of ways we could solve this, but I'm going to solve this as a linear DE. I'm going to say P prime minus KP equals 0, put it in our more standard form. Then my integrating factor, mu of t is my independent variable here, would be e raised to the antiderivative of negative k dt, which would be e to the negative kt. That's a t. So we'd multiply everything by that. Multiplying on the right, anything times 0 is just 0. So the left-hand side is the product rule derivative of the integrating factor times P. Integrate both sides. Don't forget to put your differential on both sides. That's a place people lose points. Antiderivative of 0 is just C. Over here, we get e to the negative KTP. Multiplying through by the positive version of this to make that cancel out, we get P equals C e to the positive KT. We get the same answer solving this as a separable DE. Of course, because it's the same DE. We use this for radioactive decay, where we would have a negative K value. Or population growth, where we don't have any kind of limits on our population, bacteria growing in a petri dish, and they haven't reached the boundary. So you've had a few homework problems that look like that. Our next model that we might do, there are a whole bunch we could do in between, but the next one might be maybe the logistic model. I think you've had homework problems on the logistic model. This one, however, is nonlinear. If we look at that, if I distribute this KP, I'm going to end up with a P squared. So this would be KP minus KP squared over M. That's nonlinear. So we couldn't solve this using an integrating factor. It is separable, though. We could solve it that way. So the logistic model assumes that you've got some maximum population that your environment can sustain. Like if it's bacteria growing in a petri dish, once they reach the boundary, they got no more room to expand. There's only so many that will fit. Or if you're talking about deer living in the forest, there's only so much food in the forest. There's some maximum number of deer. After that, they'll start to die off. That maximum amount is this number right here that we call the carrying capacity. And if you notice, if my population equals that number, if these two are equal, then this fraction is 1. 1 minus 1 is 0. My derivative would be 0. I've reached some point where my population is no longer growing. If my population is bigger than that number, then this is bigger than 1. I get a negative here. A negative derivative would mean my population's decreasing. Once we reach that carrying capacity, we start going down. Okay, and I included a link here. Again, like I said, I've never used this app before. I just wanted to include a link to this page, and it included the entire page here. And I don't know how to change that. But here, you can see it here. It'd be better to look at it. So this is a good overview of the logistic equation. Here's our DE. They use capital K instead of capital M on this page, and they use R for growth rate. That's not standard. Most people use capital M here for the carrying capacity. And you have a homework problem, somebody asked about it last time, that uses little k here for your growth rate and capital K here. I don't like that. Like, maybe I should go in and edit that homework question. But those are different, is the point I'm making. This is my growth rate. It's exactly the same as, really, I gotta rate you right now? Right now a 1, since I'm in the middle of stuff. So growth rate, what your population would grow like if there were no limits. That part right there, it's just like regular population growth, but then we have this extra term here that has the carrying capacity. And then here's a complete solution with numbers. I'm not going to go through the whole thing. I just want you to see here. This is a nonlinear DE, but it's separable. So they've separated the variables. They had to do a partial fraction decomposition here on this part to separate that out. And then we just do all the integrals, all the math. The interesting part is, here's our solution. And this solution is going to have a graph that looks like this. We'll start with some initial population, and if that initial population is below our carrying capacity, we'll grow up toward it, and we'll asymptotically approach it. If we start above our initial, if our initial is above what we can sustain, our population will decay. So if we start up here, we decay down toward that maximum carrying capacity. Okay, then we have the constant harvest model. So this is our group assignment that's coming up. You guys are going to solve this one. So I'm not going to go through the whole thing here. So again, it's just like regular old population growth. We've got dPdt equals some constant times our current population. That's how quickly our fish are reproducing. Okay, there is our reproduction rate. But we're harvesting some constant number every year or day or whatever our time variable is. In this case, I think we're in years. So H here is a constant number that we're taking out from the population. Doesn't depend on the population. Okay, so what you're going to do is solve this. It's separable. It's linear. I could solve this as separable and say dP over Kp minus H equals dt. I've separated the variables. All my P's are on this side. All my T's are over here. Or I could say, maybe write that as P prime minus Kp equals H. Now I've put it in kind of standard form for a linear DE, here my little P of X is negative K. I could find my integrating factor. Mu of T, that's a T. There are no X's here, that's a T. Mu of T would be E to the antiderivative of negative K dt. Okay, and again, I'm not going to do the whole thing for you. You got a couple of different ways you could solve it. So solve it. Notice, literally, I even say this here. I left all this space so that I could fit all these problems on one page here. It does not take nearly this amount of space to solve this. It's a pretty easy DE. So you're going to solve it in general. Then I'm going to run you through a few different scenarios. So plugging in all these values, I want you to sketch a graph of the solution with these values, a labeled graph. So a lot of times I get graphs that just kind of look like that's it. That's literally what people turn in. That's not a labeled graph. I should have a variable here, T. I should have a variable here. I should have a number right there, some initial amount, whatever that initial amount is. Same thing here, but something different's going to happen. See, I've changed the H value, the amount we harvest, everything else is the same. Our growth rate is the same. Our initial population is the same, but now we're harvesting more per year. You can kind of figure out what you think is going to happen there. Okay, those are to motivate the three possibilities. So you could kind of figure out what you think is going to happen here. What if the amount we start with is small compared to the amount we harvest? Or what if the amount we start with is big compared to the amount we harvest? One of these is going to give you something that looks like regular exponential growth. You're going to get a graph that kind of looks like this. One of these, your population is going to die off. You're going to get the opposite. You'll end up with a graph that goes more like this, but only smoother. One of these, you're going to get a constant amount. You can kind of figure it out, right? So you're going to look at all three of these scenarios, look at your general solution that you get up here, and deduce what these behaviors have to do long term, and sketch graphs here. Again, labeled graphs. Then in one of those, like I already kind of told you, in one of those, you're eventually going to die off. I want you to find that time right there where you die off. So you're solving for when P of T equals 0. In terms of these other variables, you're not going to get a number, you get an expression. Okay, so it takes a little bit of time. It might take you 15 or 20 minutes to do the entire problem. Okay, a couple more applications. I wanted to do free fall. So this is from your physics class. Remember, F equals ma, Newton's second law. The sum of the forces equals mass times acceleration. If I have an object in free fall, my only force is the weight that'll push down, negative mg. But remember, acceleration is the derivative of velocity, and it's the second derivative of position. So I could write this dE as m y double prime equals negative mg, where y is my position. This is a second order linear dE. Or I could write it in terms of velocity. I could say mv prime equals negative mg. velocity being the derivative of position, or acceleration is the derivative of velocity. You guys have taken physics, you know this. That's a linear dE. I could divide through by m, get v prime equals negative g. That's separable. Honestly, if you handed me this, I would think of this as dv dt equals negative g. dv is negative g dt. Integrate both sides. V equals negative gt plus c. Right, that's the easy way to solve it. But we could also solve it as a linear dE and say v prime plus g equals 0. Actually, we wouldn't want to do that. Our integrating factor here is just 1. If we solved it as a linear dE, it's literally still the same math. Yeah, so that would be too much work there. Because our P of t here is just 0. We don't have a regular V. So the integrating factor here is 0, or I guess it would be 1. Okay, but here's where it gets interesting. That's a boring problem. Let's make it more interesting. Let's do a skydiver. Jumping out of an airplane, falling to earth. We're adding in air resistance. So we're going to assume, this is called the low speed approximation. We're going to assume that we have some drag force. That's a capital D right there. Some drag force that points opposite of our velocity. So if our velocity is down, we're falling, we've got this extra force in here that points in the opposite direction of velocity. Our drag vector will be negative some beta times our velocity vector. This is actually an approximation. In the real world, this is not the real formula for drag. Drag actually goes like this, goes like v squared. But at low speeds, this is a pretty good approximation and makes this problem linear. Okay, we know how to solve this. Acceleration is the derivative of velocity. I could divide everybody by m here and get v prime. I'm going to move this term over, plus beta over mv equals negative g. I divided through by m and move this term to the left. That's a linear first order dE. We could solve this using an integrating factor. So my integrating factor, mu of t. Something else I don't like about this program is I can't control Z to undo. I have to go up and hit that undo button. On all the other note kind of apps I've used, I could just hit control Z and undo. I don't think I'm going to keep using this. Anyways, my integrating factor here is e to the antiderivative of b over m dt. That would be e to the b over m t. Multiply everybody by that. Then the left side should be the product rule derivative of v times that integrating factor. We should check and make sure, and it is, because the derivative of this guy is the same thing times the derivative of the top. Integrate both sides with respect to t. We don't forget our dt here. Left side, the antiderivative of the derivative, those just cancel out. We get this. we get what's inside. On the right side, that G just comes along for the ride. Antiderivative of e to the anything. You could do like a whole bunch of substitution here if you want, but this is really one at this point in your mathematical career that you can just do in your head. If I were taking the derivative of that, I would pick up a b over m. Since I'm doing antiderivative, I'm going to get the reciprocal of that. I'm going to get an m over b e to the b over m t plus c. I'm making sure I did it right before I move on. Yeah, that's right. And then multiply everybody by the reciprocal of this by making that a negative. And we'll get V equals negative mg, of course, is our weight, over B, plus some constant times e to the negative b over mt. There's our solution. For a person jumping out of a plane, a skydiver, we could look at this behavior. This is some exponential decay term. As t gets bigger and bigger, this goes to 0. We can see pretty much immediately. I won't go through that. As t goes to infinity, this part is going to go to 0, and v will trend toward this here. So we're going to start, say we started at 0 vertical velocity. We're just dropping out of a plane. So I'm drawing if v of 0 equals 0. We're going to get some exponential decay that asymptotically approaches this level down here, negative mg over b. We call that terminal velocity. And that is the speed when these two equal each other. When your drag force, the air resistance pushing you up, is canceled out by your weight pushing you down. Okay. There are some cool project ones we can do using the skydiver problem. We can add a little more into this. This makes a good project one. Like this is like the starting point. All right, last one I want to do, and I just didn't have time to write it in here ahead of time. Newton's law of cooling. We had a couple of homework problems on it. We're going to actually figure it all out now. So our model is, I really should look this up and make sure I'm using the same variables. Let me pause just a second. Okay, so we had this problem back in separation of variables, because this is a separable DE2. And I'm just going to use the same letters that they used in that problem. These are not standard, like that A there. Most people wouldn't use that. Okay, so the way they wrote it there is K T minus A. Okay, A here is what we call our ambient temperature. So the idea is you're taking a pie out of the oven. The pie is hot, and we put it on the counter in the air. A here is the temperature of the air, the temperature of the room or whatever that you're putting your hot thing into. T is my temperature at time. K is some cooling factor that's actually really complicated to figure out theoretically. It depends on the heat capacities of both your object and the medium you're putting it into. It depends on the surface area. Newton's law of cooling says that cooling is directly proportional to surface area. If you double the surface area, that's exposed to the air, it'll cool twice as fast. Or this K value would be twice as big. It's really complicated. So we normally find this K value experimentally, which is exactly what this homework problem was doing. This is the way we, a good example of Newton's law of cooling is on CSI, when the medical examiner looks at a body and says, this body died between 6 and 8 hours ago. They're using Newton's law of cooling. And the way they come up with those ranges is they've measured experimentally how quickly bodies cool in certain environments. And that's what you were doing here in this problem, is you measured a couple of different values to try to estimate that value K. Okay, so we're never going to worry about where K comes from. It's just something you find experimentally. We can solve this dE. We can solve it as a separable dE. I could do, for example, dt over t minus a equals k d little t. Integrate both sides and I'm done. I'm going to solve it as a linear dE because that's what we're talking about this. So I'm going to write that as t prime equals kt minus a, or t prime minus kt equals negative a. I didn't distribute my k, did I? Hold on. Let me clean that up a little bit. Oh my God, I don't like this eraser either. Look at that, like it's not erasing. There it goes. It's tiny. Yeah, I'm not using this program anymore. I know you guys don't care about that. I'm kind of talking out loud. This should be KA. Okay, so there's our P of T there. The guy in front of T without a derivative on him is negative K. So my integrating factor, what we call mu, will be e raised to the antiderivative of negative k dt, which would be e to the negative kt. So we multiply everybody by that. We got to be really careful and keep our little t's different than our capital T's. Okay, then the left side is the product rule derivative with respect to little t of capital T e to the negative kt. And we should check that, and it works. Integrate both sides. Don't forget to put your differential in here. Left side's pretty easy. We just get t e to the negative kt. On the right side, like maybe I'll do the substitution here. U equals negative k t. Then du would be negative k dt. I already have that. So then my integral could be rewritten as a e to the u du. The antiderivative, that's just e to the u. We just get e to the negative kt plus c. Yeah, because I already took care of the negative. Multiply everybody by the positive version of this to make that one cancel out. We'll get t of little t equals a plus some constant e to the positive kt. And then let's say we have our initial temperature. Let's call T of 0 the temperature of the pie when you pull it out of the oven, T0. Let's solve for C in terms of T0. So that would be T0 should be A plus C e to the 0. E to the 0 is just 1. So C is T0 minus A. So we get this model. I want to make sure I got my sign right. That should be plus, right? Yeah. Okay, so what we end up with is a graph that will look like this. We'll start at some initial temperature and we'll decay off because we're going to have the ambient temperature is less than the temperature of my pie. This is a negative number, so we'll get some negative exponential growth, which will go like decay, will decay off until this part becomes 0 and will tend toward ambient temperature. So we exponentially, asymptotically approach the temperature of the room. Okay. This game that I played here with solving for C in terms of the other parameters, this is something you're going to have to do in that harvest problem here. You're going to have to play that same kind of game. I would recommend even doing it here in the solution. So once you get this solved, use P of 0 equals P0 and solve for your C, your constant of integration in terms of that. And it'll make everything else much easier.